in the spring semester, and we are happy to have Victor Ginzburg from the University of Chicago. The title is on his first slide, Chern classes of quantizable sheaves. Vita, please.
So the whole project, so this is joined with Baranovsky, Vladimir Baranovsky, and the whole project started with a conjecture by Bezrukavnikov in representation theory related to quiver varieties. And first we tried to, well, it was, so his motivation came from quiver varieties, but he asked it in general, and then we tried to solve it, and then eventually it kind of went in a different direction. And so we did prove his conjecture, and I will explain it at the very end. But the rest is very general. So first, let me fix notation. So basically, we work with some smooth quasi-projective variety. Everything is over the complex numbers. And we fix a closed subvariety, which typically will be very singular with many components. So it's really bad. And then we're interested in a coherent sheaf on X, which is supported on this crazy subvariety. And I will assume, just to simplify notation, that the support of the sheaf actually has the same dimension as this subvariety. So it may have smaller pieces, but at least the biggest pieces of the same dimension. And then associated with such a coherent sheaf, there are two types of invariants. One invariant is the support cycle. So you just take all irreducible components of my closed set S of maximal dimension only. And then for each such component, one can assign an integer, the multiplicity of F at this component in a standard way. And then you take a formal sum or linear combination of these multiplicities with times the fundamental class of the component. So this is one invariant. And the other invariant is the Chern class of a coherent sheaf. So I will use refined Chern. So usually, if you have a vector bundle or coherent sheaf, Chern classes take values in the homology of X, but there is a refined version where one
can I slow you down a little bit?
I thought that this is kind of notation, but please stop me if you.
Yes, let me stop you. How the SIs are how the multiplicity of the SI?
Okay, yeah. So it's a general commutative algebra. So basically, let's assume that everything is affine. So our X is an affine variety. Then this S is also a closed affine subvariety. So it has some. So then we take replace sheaves, replace all our varieties just by a commutative algebra of global sections, and then so F is so then Sj global. I mean, functions on Sj is just a commutative ring, and F becomes a module. And then if you have a module, you do the following: you localize this commutative ring S. In other words, replace it by the total field of fractions.
Okay.
And then you extend scalars for F. So this is a module, and now if you extend scalars, you get a vector space over this field of fractions, and the multiplicity is simply dimension. So the multiplicity is dimension of the vector space over the field of fractions. So in other words, geometrically, it means that you pick a very general point of your component Sj, and then look at the fiber of F at this point. It has some dimension, and this is the multiplicity. So it's like dimension of the generic thing, but F is not a vector bundle. It may be a coherent sheaf, so dimension may jump at bad points, but generically there is some dimension, and that's what it is. Is that okay?
Yeah, that's fine. Thank you.
All right. And then you take, so the fundamental classes basically at the moment it means nothing. It's just you formally take this component and put it in square brackets and call the fundamental class. So far it's just nothing. Then a formal expression. Now another invariant of which is even more familiar probably is just the Chern character of this F. Now again, depending on how much are you familiar with this, I can go slower or faster. So first of all, for a vector bundle, everybody knows what the Chern character is. Now then, for a vector bundle on X, then we just use the usual differential geometry or any other definition. Then if you have a coherent sheaf, then this definition doesn't work. So what you do, you find the resolution of your F by locally free sheaves, in other words, by vector bundles. And then for each such vector bundle, one knows what the Chern character is, and then you take the alternating sum over terms of this resolution and call it the Chern character of F. So this is still if we work on X. But now there is a refined Chern character with support in S. Now the usual Chern character takes it's a non-homogeneous cohomology class in the cohomology of X. Now the Chern character with support takes its values are in cohomology of X with support in S. Now this is itself a kind of depending on how there are many ways to define it, but probably for algebraic topologists, one defines the cohomology with support as cohomology of the pair X and the open set X minus S. So S is closed, X minus S is open, and so one takes cohomology, just relative cohomology of X comma X minus S. And then there is an issue: what does it mean to to define this Chern character with support? I believe it was first done explicitly by Fulton McPherson, and I'm not going to explain the construction because it's a bit technical. But the reason this cohomology was the Chern character with support is a more refined invariant, because the cohomology of X with support in S maps into the cohomology of X, and then under this map, the Chern character with support goes to the usual Chern character.
With your ground field is what?
All the time. Complex numbers. Everything is over C. I mean, well, definitely not in positive characteristic, but you can take algebraically closed field of characteristic 0, but
I mean that you're not going to use analytic topology.
No, when I define, well, you see in my in the formula where I write CH sub I belongs to, then there's a subscript de Rham. So my definition, so the cohomology I'm using is de Rham cohomology. But since I'm over C and you can treat X just by a topological space, it takes the usual cohomology. So this is really, it doesn't matter what cohomology theory you take.
I mean, the cohomology with the supports, just that you regard that as
one has
constructible functions.
Sorry?
From constructible functions, just look at the sections.
There are no constructible functions.
Is that the same?
No, there are no constructible functions. If you are an algebraic topologist, you simply take the cohomology of the topological space X, and you take cohomology of the pair X and X minus S, and view them as topological spaces, and then use your favorite definition of singular cohomology or de Rham cohomology or whatever. And that's it. So to define this cohomology with support, just you can be just work in algebraic topology. Just the usual cohomology of X comma X minus S. One can do it in the de Rham cohomology. The only reason to do it probably is just to replace C by arbitrary field of characteristic 0. But since I don't care about it, I mean, you can forget about this de Rham. It won't matter at all. Okay, all right. So we can just stick to the usual topological setting, usual singular cohomology, and then we take the usual cohomology of a pair, as explained in algebraic topology. Okay. Is that okay?
Yeah, that's okay.
Okay. All right. So now we are interested in quantization. So now we assume that this X is actually an algebraic symplectic manifold. So it has a symplectic form, algebraic symplectic form. And then, as we know, any symplectic manifold produces a Poisson bracket on the ring of functions. And this is the initial data needed for quantization. So I remind, nowadays it's completely standard definition. So we will be working with formal quantizations, which means that we are replacing the structure sheaf OX by an algebra, again by a sheaf of algebras, which now depends on a formal parameter H bar. And so everything, so it's a completely formal quantization so there's no convergence or anything. So the algebras are just power series, formal power series in H bar. And the algebras usually are not commutative, because the whole point of quantization is to replace the functions on X by some non-commutative algebras. But modulo H bar, they reduce to functions. So it's the usual setting where we deform a commutative algebra to a non-commutative algebra parameterized by a formal parameter H bar. The only difference is that now we're working in a not necessarily, so our variety X is not necessarily affine, so we cannot reduce to algebras. And so every time, so we write O sub X, meaning a sheaf, and then we quantize, meaning just take an affine open set and quantize there, and then glue over some covering by affine open subsets. Is that okay, or should I say something else?
It's okay, but probably this time it's not a good time to ask questions.
Well, it depends on. Well, I mean, probably if the question takes a lot of time, I will.
No, I mean, I don't know. Just sort of question is that your X is quasi-projective, so certainly it's non-compact.
Yes, typically it will not be compact. But I mean,
yeah, and so there are some missed opportunities, maybe even in your main result. Okay, but it's not as I'm saying, it's not the time.
No, it can be compact. Just of course it can be compact. Quasi-projective may be projective.
No. But yeah, I understand.
But
no, I mean that if it's non-compact, then there is a possibility. Actually, it's kind of first observed by Koncevich in his second quantization paper, that you can choose compactification, and whatever you will define the category, or even just objects like coherent sheaves supported on something, it depends, the category will depend on the choice of quantization. So, but again, I don't think it's the right time.
The main example that actually came from representation theory, there is in fact a completely canonical compactification, and essentially in the application I will do exactly what you say. I will not say it explicitly, but if you look into this, you'll see that that's exactly what. So in that case, I mean, this general theory of Koncevich is not needed, but the outcome will be exactly the same. So you'll see if we get to this.
I know you are going to focus on the symplectic case, but so far the setting is for Poisson variety that should be working.
I will always work with symplectic manifolds. General Poisson manifolds never show up anywhere. I'm just saying that if you have a symplectic manifold, then in particular you have a Poisson bracket. That's all. But everything is symplectic. There will be no degenerate.
And I'm sorry to say that in general you do not have a sheaf of algebras, but the sheaf of categories. Yeah.
Oh well, okay.
Yeah. But I mean, to be pedantic.
No, I mean you can quantize to a sheaf of algebras, maybe.
Not always. No, there are abstractions.
Well, yeah. I mean, for a quasi-projective variety, there's not. I'm not trying to. I'm not proving that there. I can.
But you assume that you
have a quantization, because in all applications I already have a quantization. I want to prove something about it.
Okay.
So the only thing I will need is that, according to this general theory. By the way, maybe I should say it is important. In the case of symplectic manifolds, there is a theory of quantization worked out by Bezrukavnikov and Losev, which is not based on Koncevich at all. It's more like original Fedosov approach. So it is known how to quantize any algebraic symplectic manifold, no matter whether it's affine or projective or whatever, as long as it is symplectic and smooth. And quantize them, and the output is written right here. So there is a class which is very similar to what Koncevich says. So it can be called, I don't know, I put many names, Fedosov, Delin, Koncevich, there are many other names, and sometimes it's called the period class. So this is a class in the second homology of X. Again, you can put the RAM or whatever. and then it's a formal power series in H bar. But again, I want to emphasize that to do this, nothing what I say today depends on quantization. Just it's completely symplectic cases, much more simple. I mean, this is a non-trivial theorem, but still it does not depend on Kontsevich. There are no crazy integrals that he uses to construct this quantization. So it's Kontsevich independent. And there is a quantization. So for every such formal power series with coefficients in the second homology, one can construct a quantization. It's a theorem. All right. Is that?
Yeah. Go ahead.
All right. So now I will be interested not in the quantization itself, but in modules over this quantized algebra or sheaf. And again, a module means that it's actually a coherent sheaf of modules over my non-commutative sheaf of algebras, O sub H bar. And then, so I take this M, and I forgot to write that I probably need it to be flat over H bar, because otherwise I don't think it's called a quantization. And then somehow, if I have an object over quantized algebra, I get an object over the classical commutative algebra by dividing by H bar. This is the classical kind of original object that I'm quantizing. And so when I divide M by H bar, I get just usual coherent sheaf on X. And then the first result, which is again classical and like 40 years old, I believe, is due to Ofer-Gaber, which says that the support of the classical sheaf of this M mod H bar cannot be arbitrary. It cannot be very small. So in fact, every component, so the support may be reducible, it may have many components, but in fact, every component cannot be very small. For instance, the support cannot be a point. Never, unless X is a point. And so the only thing I will use is that it's written at the bottom of what you see, is that every irreducible component has dimension. So every irreducible component of the dimension of the support has dimension at least 1/2 of the dimension of X. So it cannot be small. And more precisely, it is a quasi-tropic subvariety, which I mean, the notion of quasi-tropic is just some property of bilinear form, symplectic form, and so which implies that the dimension of is not less than 1/2. But an important point to emphasize that the support is typically very, very singular. So each component is crazy. The components may intersect in some crazy way. So it's really nasty, usually. Okay, so now what people like most is the extreme case, which is usually called holonomic. So this is the case where the support is as small as possible. In other words, every reducible component has dimension exactly 1/2 of the dimension of X, and which is equivalent to saying that every reducible component is a Lagrangian subvariety of X. Okay, so this is what is written here. So now we take S to be this support of M mod H bar. Now every reducible component is Lagrangian. And then one can define the characteristic cycle of M. So basically you reduce mod H bar, you reduce M mod H bar, then you just get the usual coherent sheaf. And then you take support cycle as it was defined 5 minutes ago. And so it's this formal linear combination. Yes, this support cycle here, it's a formal linear combination of multiplicities times fundamental classes. Now you just replace F, the sheaf, by M mod H bar. So we take substitute, plug in F equal to this module over the quantized algebra divided by H bar. So and this is called characteristic cycle instead of the support cycle. Just change of the name, nothing else. All right. Yeah, so this is So this is the most interesting case in many areas. People like characteristic cycles. I mean, people like holonomic modules. So the first main theorem that we prove is that so now the holonomicity condition has to do with the support, with this cycle. But now I can look at the Chern classes or Chern character of the same sheaf, M mod H bar. And the miracle is, and this is our kind of key result, is that in general, if I take a coherent sheaf, then its Chern character has components in many degrees, essentially in all degrees. But the miracle is if I start with a holonomic module of the quantized algebra, take its reduction mod H bar, then I get its coherent sheaf. And then all Chern components of the Chern character vanish except just one. And this one is Poincare dual to the characteristic cycle. So the Chern character is completely kind of as small as possible. I mean, it's even, I would say, less than one could possibly imagine. And the only non-trivial component is completely dictated by the characteristic cycle. This is the key theorem, which is kind of was at some point we didn't believe in it because it's very strange that just every component of the Chern character vanishes completely except one. And this one, which does not vanish, is actually in top degree. So all components of low degree vanish, which is something, I mean, if you take a coherent sheaf in general, there's absolutely no reason for all components, for many components to vanish. Now, there is a kind of a very baby case where there is an explanation for this. And the baby case is when everything is as nice as possible. So if we assume that our Lagrangian subvariety is smooth and our sheaf is a line bundle, and sorry, I wrote F, but F means M mod H bar. Then there is an explanation, which can be done by hand. Namely, the condition that a coherent sheaf F can be quantized. So F is a line bundle on S. Now I want to quantize it. So I want to deform it mod, the first order deformation mod H bar squared. And then if I want to deform it further, it will be a deformation mod H cubed squared and so on. And formally, when I go to the formal power series, so this is my formal deformation. And then one can look at what do you need from the coherent sheaf F, just the classical coherent sheaf, in order to be able to deform it to first order. And then it turns out that the data is essentially a connection on this line bundle. So basically, it's a connection on this line bundle. And then you can ask, what condition do you need to extend my deformation to the second order? And the answer is that it is essentially the condition that this connection on the line bundle is flat. It's not exactly, so the connection is not really a connection, it's a projective connection, but we can ignore it. So roughly speaking, if you want to quantize a line bundle on a smooth Lagrangian submanifold, and if you want to quantize it to a second order, you get a flat connection. And then, of course, if you have a vector bundle with a connection, then it has no Chern classes because the Chern classes can be computed using the curvature of a connection.
And for higher rank,
we had another paper with Baranovsky where there are conditions for higher rank.
But you do not have a flat connection anymore.
No, you do. I mean, it's not quite a connection. It's a little twisted. But,
but you can choose a square root of the canonical.
Yeah, so that's why I write projective. It's exactly about the square root.
Yeah, okay. Right. But you always have a flat connection on the support if it's smooth. Yeah.
Yes, but the problem is that our support is essentially never smooth in all interesting examples. And our F is not a line bundle. It's some coherent.
No. I mean, for higher ranks, you still have a flat connection.
You still have, but there are higher abstractions which you have to impose. Okay. Now, so I just reiterate what I said, that, I mean, a basic example of quantization of the cotangent bundle. So in the case where X this smooth symplectic manifold is the cotangent bundle of some other manifold. And then the basic example of quantization is a ring of differential operator. This is my quantized algebra. And then the module is just a D module in the usual sense. And then my support is what is called the singular support. And this is typically never smooth. It has many components. Even if you take D modules on the line, the support the singular support is intersecting. Has many components with intersections. So essentially, there are examples where the support is smooth. They don't exist. So no statement involving the assumption that the support is smooth, Lagrangian, it's not applicable anywhere. So it's not interesting. So this argument with flat connections definitely is not cannot be upgraded to the general case. And so we need to do something totally different. And then for a long time, we were stuck. We didn't know what to do at all. And then the solution turned out to be to use very fancy machinery, which is called cyclic homology. I am not going to say anything about what cyclic homology is. I will just, along the way, explain what properties and what kind of setting, how do they appear, and how do we use them? Okay. So first of all, now I completely forget about my symplectic manifold. Now I go back to some algebraic variety X. And there is no I said no. So I still keep my symplectic manifold, but now there is one more step which I may want to do. Namely, I can replace formal power series in H bar by formal Laurent series. In other words, I want to invert H bar. And the meaning of it is, heuristically, when I do not invert H bar, then somehow I am in a neighborhood of the point where H bar is 0, which is the classical setting. But when I invert H bar, so then H bar is no longer allowed to be 0. And this is kind of a purely quantum case where the classical case is no longer, is kind of forgotten, because H bar cannot be set to be 0. And so we're always away from the classical setting. And sometimes it's going to be important. So that we're in a purely quantum world. There's no classical limit anymore. And now to define this, to use cyclic homology, I need to introduce some fancy things. If you are not, so I will say words, but if you are not comfortable with this algebraic, I don't know how fancy stuff, you can just take it as a black box. So now the point is that originally K-theory, originally cyclic homology was defined for algebras or rings. So this is some kind of procedure which associate to a ring some invariants, which are called cyclic homology. Maybe a more familiar invariant is Hochschild homology. Again, it's computed using some complex, Hochschild complex, and just as start with a ring, build some complex and compute homology. Cyclic homology of an algebra is also computed in such a way. There is an explicit complex and you just compute homology, but this is not applicable in our case because first of all, we deal with sheaves. And so there's no algebra, and the complexes used for algebras cannot be upgraded to sheaves because one cannot glue them in any reasonable way. But people, during the last maybe 20 years, figured out what to do, and they extended the notion of cyclic homology and Hochschild homology to categories. So in fact, if you have a reasonable category with some reasonable behavior, then one can assign, again, cyclic homology to this category. And in the case where the category is the category of modules over a ring, you go back to the original definition. So, this was worked out by Bernhard Keller in the setting that we're going to use. This formalism was worked out by him. But so basically for now, so there are two theories. One is called negative cyclic homology, and the other is periodic cyclic homology. And then they are associated to modules over the my quantized algebra A, supported on my closed subset S. So I cannot really say anything rigorous, anything more rigorous, but if you have some kind of questions to get a better feeling of what this is about, please ask me. It's a good point where to ask. Hello? Do you hear me?
Actually, there were also like 2008 Maxim's lectures. It's called Levshit's lectures, where he, of course, if you pedantic about the words worked out, maybe it wasn't worked out, but it was kind of written with Chern characters.
Yeah. So now there is an issue here, or maybe I should say it, and this was a big issue for us. Namely, there's absolutely no problem to define Hochschild and cyclic and whatever homology of a category. There is a very simple way to basically mimic the definition for algebras. But also, one can still use a totally different definition. One can try to use the definition for algebras in terms of an explicit complex, and there's a way to sheafify it. So to kind of extend this definition using the complexes to sheaves. And then the question is, do you get the same thing? And this is really extremely difficult. It's a theorem by Killer, and the proof is uses it uses lots of complicated stuff. It's really hard. And for instance, it uses Thomas on Trouble, which is a very famous paper in K-theory with many. So it really uses very sophisticated tools from homotopical algebraic geometry. Because a priori categorical definition is given in the language is just take objects of the category and do something with them. But in this other definition, you really construct an explicit complex which has nothing to do with any objects, and then basically you compute some cohomology. And even for the affine variety, where both definitions are applicable, it's not completely obvious why do you get the same thing. So there is an issue, and our proofs are based on this other definition. So, and there's also an issue, a strange issue. If you use categorical definition, as Maxim did, then it's defining Chern character takes 1 minute. But with the other definition, simply people don't know how to define the Chern character at all.
So the other one, when you sheafify locally, and then
this is the one we need in order to do computations, because with the categorical definition, there is no way to compute anything. So it's not. It's very nice, and it produces Chern character. No, but we want to essentially compute it. So we take a quantization. I want to compute negative and periodic cyclic homology of this quantization. And categorical definition doesn't tell me anything about it, just literally. You cannot get started. It's not clear. I mean, you have to, in this categorical definition, they have to take all objects of your category, take all homes between them, and then construct something. But obviously, we cannot say anything about all objects of our category and about all homes between them. So this is just tells us nothing.
Victor, I do have a question about the support of the cohomology sheaves. That the cohomology sheaves are still A modules, which is quite large.
Yes, but for any, sorry, yeah, I should have said it more carefully. So there are two notions of support, which actually are the same. Just one notion of support comes from, algebraic geometry or commutative algebra rather. So if you have a module, then you can define its support as it is done in, let's say, a T. McDonald. You take the ideal which kills this module and then take zeros, essentially.
I mean, the ideal is inside of O, right? Just basically restrict the sheaf as an O module.
Well, no, this definition is not applicable to my setting, because this definition of support in commutative algebra really needs a commutative algebra. So my
That's
algebra
right.
curly A is not commutative, so this definition doesn't apply at all. But there is another definition of support for an arbitrary sheaf, completely abstract, without any commutative algebras. And you simply say that if you have a sheaf, you can restrict it to an open set. And then the support is, and sometimes if you restrict an open set, you get 0. And so now you take the union of all open sets for which you get 0, and the complement is declared to be the support.
Okay.
This definition
Yeah, that has nothing to do with the structure sheaf.
and there's no structure sheaf. No, it's just an abstract sheaf.
Topological. It's a
Without
topological
any structure. It still makes sense to ask whether it's 0 or not, if you restrict an open set. So you take the maximal closed subset so that the complement, the sheaf is 0. This makes perfect sense. And this is what I'm using here. If your sheaf is actually a sheaf of modules or a commutative algebra, it does give you the same as the previous definition, but I don't care. So this is what the support means here. And there's a word, this perf means perfect, but if you can just forget about it. So this is some reasonable category of modules over my quantized algebra A. All right. Now, here is the key point in the main theorem. So the main theorem was not the theorem about Chern classes that my theorem 1, but it is deduced from the main theorem, which is here. And the main point is written down here. So, you can ask, so we have this, we have the structure sheaf OX, which is just a commutative algebra, and it controls my algebraic geometry of X. And now we have this quantized algebra A. And now you can ask what happens if with these cyclic and periodic cyclic, whatever homology, when you quantize. And the answer is as written. So if you quantize so for the periodic cyclic homology, essentially nothing happens. Periodic cyclic homology of the classical algebra OX is the size is the same as periodic cyclic homology of quantized algebra. And moreover, this is a standard well-known result, is that in fact periodic cyclic homology of OX is actually the usual cohomology of X in the topological sense. So if we compute this periodic cyclic homology defined in some complicated way, for the structure sheaf, you just get back, it's a theorem, but it's known, well known, that you get just the ordinary cohomology of X. And the point is that if you quantize, the size doesn't change. So the size of periodic cyclic homology of the quantized algebra is essentially the usual cohomology of X.
It's kind of because of this Gauss-Manin connection.
Yes, essentially it's Gauss-Manin connection. But the key point is that if you go to the negative cyclic homology, then the situation is totally different. Quantization kills about 1/2 of the size of the classical story. And we didn't know that, and I don't think anybody observed that. And this is key, that under quantization, periodic cyclic homology moves in a very nice way. But if you go to the negative cyclic homology, it shrinks very dramatically. Essentially, half of the degrees where the classical homology may be non-zero, they die.
So say it again, half of even degrees of what?
You'll see it. There's a main theorem, it's a big diagram. Okay, so 2n is, so X is symplectic, so its dimension is even, and so n is half dimension, and this is what happens. So first of all, we prove that both periodic and cyclic homology are isomorphic, can be related to de Rham cohomology, and that's why I'm using this explicit definition of what cyclic homology is in terms of complexes. Because this, you see, this is an explicit description of cyclic homology of the quantized algebra in completely classical terms. So if you use definition using categories and homes between objects, you see that it's completely impossible to get such a isomorphism. It's a real computation. So with bar complexes, essentially. I mean, the proof is now goes by a standard strategy. You look at the jet bundles. It's formal geometry invented by Gelfand and Kashdan. And so you reduce to jet spaces, and then you reduce to essentially a quantization to the Weil algebra, and then try to descend it back to the original X. So the strategy is kind of known by now, but to implement it in this case, it's not so easy. And especially so the bottom line, it's the line where nothing changes. So the classical homology of X goes from zero, lives in degrees from 0 to the real dimension of the manifold. So the real dimension of the manifold is 4n, because the complex dimension is 2n. But we are only interested in even cohomology, and so I goes from 0 to 2n, and then 2i goes from 0 to 4n, as it should. So periodic cyclic homology of the quantized algebra lives in all possible degrees of the classical cohomology.
Sorry, Vitya, and this first horizontal line, the isomorphism, does it use kind of a twist by the square root of the third class?
I didn't say what the isomorphism. I didn't say at the moment.
Yeah, that's my question.
I will say it because I will use it next.
Okay.
But for now, all I want to say is that first of all, we identify. I didn't explain what the isomorphisms are. I will say it in 5 minutes.
So roughly, it's taking some non-commutative Chern class.
Yeah, I mean, it will be involved. You'll see. But the point at the moment is that for negative cyclic, I mean, we can compute both. And for negative cyclic homology, you see that the degrees goes from 0 to half of what they probably could go, potentially, but they don't. And this is key to everything else. And I don't think this was known before. And this is based, so I don't say, I mean, we learned about this somehow by trying to understand some papers by Nest and Sigan. And so it's my personal kind of comments.
Yeah, maybe it's not known before, but we had some kind of, with Maxim on this unfinished project, we have somehow of the definition of what does it mean that the object in this deformation quantization category has a dimension of the support, or has a fixed codimensional support, like codimension k. And the condition, it's similar, but we also impose one condition of the top degree, that it should be realized by an effective cycle.
But I'm not sure I understand. In this setting, there is no issue. I mean, the support is just reduce your quantized module by h bar.
No, you cannot reduce it because you already inverted h bar.
No, but yeah, that's right.
You should use some non-commutative kind of Chern class.
Oh, but yeah, you are right. Yes, in this way you cannot. I mean, there are certain things what one has to do. Okay, but let me skip it. Okay. When I say perfect, when I defined what is my category, I cheated. One has to do it more carefully. In the case of D modules, essentially, one has to put a condition similar to regular singularities, close to it. But let's not go into this. Okay. And in any case, it won't play any role below, because eventually I will be interested in modules where h bar is not inverted, because that's the one is essentially what one does in reality. For instance, in representation theory, you start with a commutative object and then you try to deform it, and you want to say something about it. So you never need to invert h bar. At least, I mean, you'll see. So
go ahead. You're the speaker. Yes.
So at the moment, the theorem says that there are isomorphisms, but in the next statement, I will say something more concrete about what these isomorphisms are. I will stay exactly as much as I need. Okay. And this is right here. So now I want to discuss how all the main theorem is related to the Chern character. And this is something what you predicted essentially. So first of all, for any category, using this abstract definition in terms of categories, one can define the Chern character from the Grothendieck group of the category to the negative cyclic homology. And the point here is that the target is not some cyclic homology, not periodic cyclic homology, but really negative cyclic homology. And this is the one which drops in size. So this is the correct Chern character is defined in this way. And again, it's defined using categorical definition. I don't know, and I believe nobody knows how to define it in terms of explicit complexes. For algebras, there is no problem, but this definition of Chern character does not sheafify. So it's I don't think it's known how to do it. Okay, and now we have a so now what we are interested in. So there are two maps. So first of all, the map from the Grothendieck group of my quantum category to the cyclic homology of the same category, and you can call it I call it CH H bar because it's about quantum, my quantum algebras. And now in the theorem says that this is what the theorem says. So we have a map from this negative cyclic homology of A, the quantum cyclic homology, to the, so it's the diagonal map to the object, the object we will look at to the homology of my variety X in the ordinary sense. So this is my map psi. And so my interest is in looking at the composition. So I take a sheaf over the quantized algebra, I look at its class in the Grothendieck group, and then I first apply the non-commutative Chern character, and then I go to the ordinary homology, because eventually I'm interested in something which lives in the thing that I understand, namely the homology of, and there's a typo, the homology of X instead of S with support in S. So it's the same group as all time before. So the homology with support. Okay, and now this is our next result. This is what Jan expected. So the relation between the quantum Chern character and the classical Chern character is given by this formula. There is a Todd class, more precisely, there's this A hat genus of Hirzebruch, which is almost the Todd class. The formula is slightly different, it doesn't matter. And also there's another correction, namely this exponential of C of OH bar. This correction actually keeps track of what quantization do I use. It depends on what quantization do I use. And this is this class of Delin, Fedosov, and Kontsevich, which controls, which parameterizes my quantization. So the upshot is that the quantum Chern character under the isomorphism of the theorem, of the main theorem, corresponds to the classical Chern character with two corrections. One is the Todd or Hirzebruch A hat genus, and the other is exponential, some exponential of something which controls the quantization. Is that okay? Hello?
Yes, it is okay. Yeah, we have like 22 people.
Okay. Well, I mean, I'm afraid because sometimes I lose.
Yeah. You're still connected, so at least I can hear you.
All right. So but somehow once you prove the main theorem, the formula is not really difficult. So somehow the problem is, somehow you see that in order to formulate any connection between quantum Chern character and classical Chern character, you first have to identify quantum cyclic homology with something classical. And until you do that, there's no way to formulate any statement. So the main difficulty somehow is to construct horizontal isomorphisms here. And then one can ask what happens with Chern characters under these isomorphisms. So, and this is, once you have constructed the isomorphisms, deducing the formula is not very difficult. This formula is a kind of type of Riemann-Roch theorem. And so one has, there is some proof, but it more or less all the steps are sort of known to some extent. All right, so now I'm going to a generalization of my vanishing theorem. So in fact, the cyclic homology allows to generalize the vanishing theorem from the beginning to the case where my module is not holonomic, so the support is not necessarily Lagrangian. So there is a generalization to any module over the quantized algebra. And I apologize for many notation. So basically, I don't know, since I send you a PDF, maybe a good strategy would be just to skip everything and explain what happens. Explain the proof. So this is the proof. And it's a proof of the general statement and of the Lagrangian statement as well. So the statement is this. So the proof is, once you are at this point, the proof contains 4 lines. And namely, we know by the formula that the usual Chern character of my quantum M divided by H bar is related to the quantum Chern character by this formula involving this A hat, Hirzebruch genus, and this exponential. But now psi is a map from the negative cyclic homology of the quantum algebra to the usual cohomology of X. But by the main theorem, the negative cyclic homology of the quantum algebra just does not live in some degrees. In those degrees, there's no negative cyclic homology of the quantum algebra. So psi cannot create anything in those degrees, no matter what happens. And therefore, the left-hand side vanishes in those degrees. And now the terms, the exponential of C and A hat, they're invertible because they start, it's a certain expression starting with 1. I mean, for the exponential, it's clear, it's 1 plus C plus C squared over 2, etc. And this, if you look at the formula for A hat, again, it starts with 1. So if you know that the right-hand side is 0, then the Chern, so then the factors e to the c and a hat are invertible, and so you get that ch of m mod h bar is also 0 in those degrees. That's it. So this proves that the classical Chern character of m mod h bar vanishes in many degrees. In the Lagrangian case, if you look, what you get is precisely the statement that it vanishes in all degrees except 1. So this is the trick. So in fact, what the original statement about vanishing of quantized sheaves, essentially it's not a statement about quantized sheaves, it's a statement about, it's a property of cyclic homology of a quantum algebra. A strange property that negative cyclic homology shrinks. So this is basically, this is everything I wanted to say about vanishing theorems. Now it's a good place again to. I'm going to go to now to applications to the original conjecture by Bezrukavnikov, which is a totally different stuff. So if you have something, if you would like to ask something about what I said until now, it's a good point to ask.
Maybe not ask. Well, it's a mixture of a question and comment, and I cannot separate what is a question and what is a comment. There is a kind of from the point of view of mirror symmetry, there are people in the audience who are interested in mirror symmetry. So this is a kind of one side of the story, and there is another one, at least in the Lagrangian case, in the holonomic case. And this is interpretation in terms of Fukaya. So there is this conjectural Riemann-Hilbert correspondence of Maxim and myself, which says that category of holonomic objects defined properly is equivalent to the Fukaya category of the same symplectic manifold. And so then still there is a problem with singular support, because conventionally on the Fukaya side, people consider it only Lagrangian submanifolds, but there is a way to handle this and to at least in this algebraic setting, to define Fukaya category, which includes Lagrangians with singular supports. And then simply the question would be, if you consider this quantized coherent sheaf, what is the corresponding object on the Fukaya category, and whether this vanishing condition becomes kind of
it's not a condition.
Manifest.
It's a property. It's not a condition.
No. You have a classical object, a coherent sheaf, yeah, and you want to say that it's quantized. It can be quantized. So there
no,
is.
I think if your support is singular, you cannot possibly. It's known from representation theory that it's impossible to give an answer. I mean, it's a long story.
I do not know results which says that it's impossible to give the answer.
No, essentially it's a theory. No, it's a theory. Basically, I can tell you, maybe this will convince you, it's equivalent to trying to classify unitary representations of your favorite group. And as we know, this people try to do this for almost 100 years, and there's still no solution. This is exactly where the problem essentially is. I mean, part of it. So if you were able to say,
all right. Okay. Let's then go. Yeah, I understand. Let's then go indeed from quantum to classical. So you just say that if you take mod H, your quantum object, you already know that it exists. Let's forget about this.
So in applications, we already have it. The question is, and then there's a striking statement that the classical objects have almost no Chern classes.
Yeah, the classical object, which is a kind of support in some sense of your quantum object.
It's not a support, it's a coherent sheaf. It's still, and then you can take the support. No, the support, the coherent sheaf may have many Chern classes. And the support cycle is only one, the top one. But in principle,
so anyway, it's a restriction on the Chern class of the object, which is a quasi-classical limit, I don't know how to say, of your quantum object. Is it correct? Good.
Yeah,
now, this quantum object corresponds, in case if it's holonomic, of course, it corresponds.
You can take mod H, you get a coherent sheaf.
That's okay, but you have some vanishing condition for this.
Even if it's not holonomic, it's just not as nice. It's written in the PDF, so I don't think it's a good idea.
Yeah. But I'm talking just about the holonomic part, that there should be a similar statement. Similar I cannot clarify. Analogous statement in terms of the Fukaya category, and maybe this vanishing condition will be kind of more understandable, because on the Fukaya side, roughly speaking, you will have sort of a constructible sheaves supported on this singular Lagrangian.
But you see, it's a statement not about sheaf, it's a statement about cyclic homology of the category. So you can take the Fukaya category and try to prove that negative cyclic homology sits in half degrees that one possibly could expect. So it's a statement about the categories. The sheaves don't play any role.
It's a category of objects with some restriction on the support. Is it?
Well, you can. The restriction on support simply because we're interested in this setting. But it's stronger.
No. It's important because your S for holonomic, it will be a kind of singular Lagrangian. Is it correct?
So
that's why I mean that this category of holonomic objects, in some sort supported on a given singular, it should have some meaning in terms of the Fukaya category of the same.
Maybe now I want to go discuss applications, because at the end,
it's already it's rather a discussion.
A proof which involves Wedderburn theorem from undergraduate algebra, and so I want to get to this point. There will be no Fukaya categories, so I think it's fun There will be a short proof with 5 lines, but it goes down to Wedderburn theorem, which I believe I like it. Okay, so now the applications involve a setting which is very familiar nowadays in representation, in geometric representation theory, but maybe not so familiar to you. So I just remind you very quickly what happens. So we start with the same smooth symplectic manifold as before. And now, first of all, for any algebraic variety, affine, projective, quasi-projective, whatever, one can consider an affine variety by just taking all global functions and then taking the spectrum of this algebra. If the variety is projective, then there are no global functions, and so the spectrum will be 1 point. So it's not very interesting. But in the situation I'm interested in, there are global sections. They don't determine X itself because X will not be affine. But one can still go take the algebra of global sections, take the spectrum, and this will be an affine variety. And this variety is called the affinization of the original X. So it's always an affine variety. And why one always has a map from X to Y, tautologically, if you have, since both of them have the same ring of functions, it follows that one has such a map. So for any variety, one can consider its affinization, and there is always a map from the original variety to its affinization. That's all. Now, the situation I'm interested in is very special, and this is called conical symplectic resolutions. And this is the situation where I have three properties. First of all, as before, X is symplectic, algebraic symplectic. Now, this map to the affinization is birational and proper. So essentially, it says that this map is a resolution of singularities of Y. So typically, although X is smooth, Y is very singular. Again. So this map is a kind of resolution of singularities. In addition to it, there is one more structure. We require that there is a C star action on X, and it acts on the symplectic form with a weight. So it rescales. So the symplectic form is not invariant under the C star action, but rather the C star action rescales symplectic form by a certain factor, by a weight. And an important requirement is that the weight must be strictly positive. So if the weight m were 0, that would mean that the form is invariant under the action, and we don't want that. And the weight negative will be opposite to positive, but we want it to be positive. This is just the setting. I will give 3 examples, and which are probably, hopefully familiar, and in those examples, this is true. And finally, so if you have a C star action on X, automatically you have an action on the algebra of functions, and therefore an action of the same C star on the affinization variety Y. And the last condition is that the action on Y contracts Y to a single point, and this is a fixed point. So this Y looks like a cone, and the action contracts everything to the vertex of this cone. Okay. Now I will give 3 classic, kind of the most well-known examples, and maybe this is this gives you some idea what this looks like. So the basic example, well, I don't know what is basic here, but somehow an example of the smallest degree is that, which is called Kleinian singularity. So you take a finite subgroup in SL2 or SU2. This is related to Platonic solids. And then this group, since it's a finite subgroup of SL2, it acts on C2. We can take a quotient. It's a surface, and it has singularity at 1.0. And then this surface has a resolution of singularities. And it turns out that the resolution is a symplectic manifold, and everything satisfies the axioms that I wrote before. And the C star action is just the action on C2 by multiplication. So I believe here everything is very clear, maybe except that this resolution has a symplectic structure, but it does. So this is kind of a basic example. The second example is also very classical. So you take n points on the complex plane, and then one has the Hilbert scheme of endpoints on the complex plane. And there's and the corresponding Y. So the Hilbert schema is not just a collection of points, it's an ideal, it's a more refined data related to the ideal whose zeros are those points. But one can ignore the ideal, and then one just remembers the points. And then if you have unordered collection of n tuples of points on C2, this is C2 to the power n mod, the action of the symmetric group by permutation of the points. This is singular variety. And it turns out that this Hilbert schema is a resolution of singularities. The map, this is very classical, as you see, well, Hilbert comes from Hilbert, and the map pi, which is projection from X to Y, is in this case called the Hilbert-Joule map. So this is something from textbooks on the Hilbert schemes. And then both of these examples are covered by the very general setting, which is called Nakajima varieties. I'm not going to say anything about what it is about, but in this situation, Nakajima varieties are constructed in terms of quivers, and then they use some quotient, and there are two ways to take a quotient. One can take a categorical quotient, which is kind of most standard quotient in algebraic geometry, or one can take a GIT quotient, and this involves a choice of stability condition. And there's just the GIT theory says that there's always a map from a GIT quotient with non-trivial stability to the GIT quotient with zero stability. And in many cases, not always, but very often, this map turns out to be a symplectic resolution in the sense I defined above. So, I mean, this list can be, I mean, I can give lots of other examples of this. So there are many interesting examples of this kind, which are very important in the representation theory, which fit into this general framework with three axioms, where one has a birational proper map where X is smooth symplectic, Y is singular, and there's a C-star action which contracts with this behavior. So this is just
for you, all three are important. Like, for example, not every transversal slice.
I mean, you can take the Springer resolution, you can take transverse slices, which are called W algebras in the quantized world. And there are many other examples. But I mean, the first two examples written down are just special cases of Nakajima varieties.
For you, important that it's really a resolution. It's a symplectic resolution.
Yeah. Yes, this is true. So basically, yes, it's completely, I mean, this is.
Okay, so you need the C-star action in your symplectic manifold.
Yes, and C-star action, I cannot, well, you'll see in a second how does it show up. And in all these examples, the C-star action is obvious. Somehow it's the most natural action you can think of.
I mean that not all Coulomb branches are symplectic resolution. That's
no, not all. But
yeah. But you really need this. Okay, good.
I don't talk about Coulomb branches. I'm talking about symplectic resolutions. All right. So now this is more or less the answer. Why do we need a C-star action? And this is important. It's easy to explain and important. Now, in the presence of C-star action, I'm a little bit cheating. Basically, C-star action on a variety gives a grading on the algebra. This is something basic. In our cases, this is a little bit more subtle because we don't really have an algebra. We have a sheaf of algebras, O sub x, because our variety is not affine. But still, somehow you should think of it as a grading in some sense. And if you, so now the variety that we're quantizing is a Poisson algebra with a grading. And in this case, you can do better. Instead of formal quantizations over formal power series in H bar, you can do things in a more kind of concrete way. So you can ask for deformations which have a filtration such that the associated graded is the original algebra. In other words, instead of modding out H bar, in other words, setting H bar to be 0, you can take associated graded. It has the same effect. The most familiar example of what I'm saying is you take the Lie algebra, you take the enveloping algebra of the Lie algebra, And then the associated graded is the symmetric algebra. This is Poincare-Birkhoff-Witt theorem. And then you can think of the enveloping algebra as a deformation or quantization of the symmetric algebra. But it's not an arbitrary deformation. It's a deformation with filtration. In this case, you can take the associated graded. And from the point of view of deformation theory, this means that you can set h bar to be 1 or 2 or whatever, but it's not a formal variable. You can really specialize it to any number you want, because associated graded is a concrete. It doesn't matter for which number you specialize. All non-zero h bars will give the isomorphic algebras. So there are only two cases: either h bar is 0 or not 0. For h bar 0, you get the classical algebra. For any other h bar, you get the quantum algebra, always the same. And this is my curly B.
Vita, I'm a bit confused. Is it equivalent to the choice of C-star equivariant compactification or something like that?
Yes, that's exactly the point. You might, so this conical symplectic resolution has a natural compactification. Basically, it's the same way as how you compactify a vector space. C-star action allows you to define the notion of a projective space, Pn. So you compactify Cn to Pn plus to Pn. Add the divisor. I mean, there's a very nice smooth divisor at infinity. You can do it here, but it doesn't help. So you can do it, but I don't see. Somehow using filtered quantizations, it has the same effect as compactifying. It's essentially equivalent. I'm going to explain it, but to consider not formal quantizations, but this filtered quantizations where you really, where h bar is no longer a formal parameter, is essentially the same thing as compactifying.
Yeah, actually, this was Maxim's idea in his paper of 2000.
Yeah, maybe, I don't know if there are any algebraic geometers in the audience, but when I came to this point, I learned something which I never knew before, and this is very surprising. So it turns out that there is no notion of de Rham cohomology with compact support. Just if you look at the literature, there's no such notion. There's no definition of de Rham cohomology with compact support. And therefore, there's also no notion of Hochschild cohomology, cyclic cohomology, or whatever cohomology with compact support. And the reason I'm mentioning it here, that in the case where you do have such a nice compactification, this notion can be defined. But in general, it's very strange that nobody ever defined, for instance, de Rham cohomology with compact support in an algebraic variety. There's no such thing, which is strange. So you might want to. Okay, so now since I'm completely out of time, let me get to this main application, and I want to really explain the proof. I mean, sketch the proof because it's really nice. It's very short. Okay, so now, well, in this case of filtered quantizations, again, one has a complete parameterization, and now there is no h bar. They are parameterized by a very nice space, namely just the second cohomology of X. It's a finite dimensional vector space. No power series, no nothing. In all these examples that I mentioned, the parameterization is explicit. The H2 can be computed, and it's known how to parameterize given an element of H2 of this, for instance, Lagrangian singularity or Hilbert scheme. It's known how to deform, how to quantize. So everything here is, at least in all examples, is very concrete. Okay. So now, because we're dealing with filtered quantizations, we have no h bar. We have this sheaf curly B of associative algebras. We can take global sections, and then we get an actual associative algebra. Just an associative algebra without any h bar, just literally. And now if it comes with a filtration, because this curly B was filtered. And the associated gradient of this algebra is isomorphic to the algebra of global functions on X. And it is also isomorphic to the algebra of global functions on Y, because by definition, Y was affinization of X. And so by definition, these X and Y have the same algebra of functions. Okay. So you should think of this straight B as the enveloping algebra. Well, in the enveloping algebra case is not the case of symplectic resolution because there's nothing symplectic. But roughly speaking, you can think of B as an example, as an enveloping algebra, and group B as a symmetric algebra. So this is more or less what happens. And in all those cases, this algebra B can be again described, well, not very explicitly, but it's a very concrete object. And the representation, the reason, so basically geometric representation theory at the moment is interested in representation theory of the algebras B for all these examples. That's more or less, if you look at any paper on geometric representation theory, it has to do with some of these Bs. And these Bs are also appear as Coulomb branches for some particular settings. So this is what representation theory is about. Now it's we have some nice collection of lots of examples of interesting non-commutative algebras B, and we study representation theory of those B. So this is the relation, how they appear in the representation theory. Now we want to study modules over this algebra B, but we want to study modules which come from geometry, and modules coming from geometry appear in this way. You first take a sheaf of modules over this sheaf of algebras curly B, and then you take global sections. So the modules we're interested in appear in this geometric way. This is, if you know, in the D module setting, this is the setting of Beilinson-Bernstein, where we start with D module and then we construct a representation of the algebra we're interested in. So this is exactly the same procedure. We go from a sheaf of modules to the module, to the global sections, which is a module over our concrete nice algebra. Now, but if you have a sheaf of modules over the curly B, we can still look at its characteristic cycle, which is the same as this all the notions I introduced before. It was called the support cycle, or then divided M mod H bar. In the case where everything is filtered, this is called characteristic cycle, but it is the same object. Dividing by H bar, setting H bar to be 0 here corresponds to taking associated gradient. So it's essentially the same thing. Okay, so now here is what Bezrukavnikov conjectured and what we proved. So the conjecture is the following: start with sheaf of modules over this curly B of the quantized algebra. And we are interested in the case where the modules over the actual algebra B are finite dimensional and simple. We are interested in, as in representation theory, we want to study irreducible representations. And the basic ones are those which are finite dimensional. So we look at the curly B modules, the sheaves, such that the global sections are finite dimensional and simple. And then the statement is that if you take, these finite dimensional simple modules are non-isomorphic, then their characteristic cycles are linearly independent. So in other words,
linearly independent as elements of...
I will say it will be below in 3 lines.
Okay.
Okay. So this is a statement, very simple. Now, for instance, a typical example will, the first example of all these symplectic resolutions, which appeared in representation theory, is the Grothendieck-Springer resolution, Springer resolution, which corresponds in the setting to Beilinson-Bernstein D modules. And then if you look, the case of finite dimensional representation here is a little bit degenerate. But then if you look, for instance, in category O, then the statement is true. The characteristic cycles are indeed linearly independent. But it is proved by a in a combinatorial way. It's not difficult, but it's a property of the Weil group. And so it's not a geometric property, even in that case.
Yeah, but there is sort of an empty example to this non-trivial statement when you take this line bundles on smooth Lagrangians, and so by Kashivara-Shapira, the simple objects.
Well, the Lagrangian variety is compact. if it's not compact. I mean, they're simple, but they're finite dimensional only if
no. I mean, there is this kind of, as I'm telling, it's almost non-example, but there is a result of Kashivara, I think, Shapira, sort of obvious that if you have a smooth Lagrangian, so then to align, there is a canonical simple object which corresponds to it in the quantized category, which corresponds to it. So basically, if you have different Lagrangians, then you have non-isomorphic simple object.
The point is, I will get to this point that so maybe first I want to prove this theorem because the proof is 3 lines.
Okay.
And so now the first observation, this is somehow maybe explains what you just said. So in fact, it's known that, so in this symplectic resolution, x goes to y. Where is it? Here, in the general definition. So we have this x goes to y. But now by the axioms, we have a C star action which contracts y to a single point. And this point is denoted by 0 because in all examples, it is indeed 0 in any sense you can make. So in this, for instance, C2 Mach gamma, it is 0 in C2. And also here, you take 0 in C2 and take n, I mean, all the time 0. So it's always clear what is this 0. Now, since you have a projective, this birational proper map pi, then the pre-image of 0 is a projective variety. This is kind of, and this variety is usually Lagrangian, but it's usually very singular. It has many connected, many reducible components. Each component is extremely singular, and in all examples, in the example, even in this example, in the example of Kleinian singularity, the 0 fiber, it has many components. Each component is a copy of CP1, but they intersect. The number of copies depends on the group gamma. In the case of the Hilbert scheme, there is one component, but it's very singular. And in the case of Nakajima varieties, it's so complicated that there's no way to say what is. But the point is, the theorem is that it's a theorem that the dimension of the fiber is not greater than 1/2. And in all examples I show here, it is in fact Lagrangian. So it has many components and each of them is Lagrangian. So this is a typical picture. So the case where, and this is the variety I'm interested in. So it's the 0 fiber of this map. So the case where this is smooth Lagrangian, basically, I don't know any case where this is true. So the case of smooth, in the case of symplectic resolutions, is completely empty statement.
And it doesn't have to be reduced. I mean, sort of, do the components have
no? I mean, it's a 0. The scheme theoretic structure doesn't matter here. Usually, I think it's never reduced. But from the point of view of what I'm doing, since I'm taking, well, I don't know. So I don't think. I believe it's never reduced, basically, in all these cases. So yeah, so if you try to study it as a scheme, it's hopeless. You don't want to do this, it's just hopeless. And so the characteristic cycle, in my case, yes. And so an important thing is that if you require that the module of global sections is finite dimensional, it's equivalent to require that the support of my sheaf sits on the 0 fiber. It needs to be proved, but it's a fact. So the characteristic cycle is simply you take irreducible components of the 0 fiber, and each component comes with some multiplicity depending on your module M. And the claim is that if your modules are irreducible and finite dimensional, then the corresponding characteristic cycles, the linear combinations of the same components, are all linearly independent. That's the statement. In particular, if there's only one component, there can be only one finite dimensional representation. In particular. So this is the statement. So Bezrukavnikov and Losev use this statement in a special case of special varieties. And Bezrukavnikov kind of asked, in what generality is this true? And now the claim, we prove that it's true in full generality for any conical symplectic resolution. Okay, so now final step, I want to prove it. So the proof involves 3 steps. The first step is undergraduate algebra. If you have a module, a finite dimensional module over the algebra, over an algebra, you have a notion of trace. The trace is a linear function on the algebra. Namely, you take the trace of the action of your element in this finite dimensional vector space M. Very clear thing. Now then, classical Wedderburn theorem about the structure of that any finite dimensional semi-simple algebra is a direct sum of matrix algebras implies as an exercise that the traces of irreducible finite dimensional representations are linearly independent. So this is an exercise. Basically, you observe that since we're talking about finite dimensional representations, it doesn't matter whether the algebra B is infinite dimensional and complicated or not. It acts always through a finite dimensional quotient. And now a finite dimensional quotient is a finite dimensional algebra. And then one can apply the theory of finite dimensional algebras. And everything reduces to, by Wedderburn, to a direct sum of matrix algebras. And for this, you check this claim by hand. We know what are simple modules over a matrix algebra. And over a direct sum of matrix algebras, you compute the trace and see that they're linearly independent. So this is undergraduate algebra. Okay, the second step is kind of Riemann-Roch. Namely, if you're, now we go back to the case where your module comes from a sheaf over some sheaf of quantized algebras P, then if you take global sections, Riemann-Roch tells you how to compute the trace in the previous sense in terms of the Chern character. This is not very surprising because Riemann-Roch says exactly that. Expresses the trace in terms of the Chern character. And now the final step is that our main vanishing theorem says that in the situation at hand, the Chern character, all components of the Chern character are zero except one. And this one is Poincare dual to the characteristic cycle. Now we're done, because if the characteristic cycles are linearly independent, then the Chern characters are linearly independent, and therefore the traces are also linearly independent. But they are not, because for irreducible finite dimensional representations, they are not linearly independent by finite dimensional algebra. So this is the concrete application of our very sophisticated stuff involving cyclic homology.
Vita, this finite dimensionality, which you said it helped to reduce, I mean, it forces to reduce to this component. How, I mean, what's the reason?
Well, I don't know. Well, the original motivation came from work by Bezrukavnikov and Losev. And in that paper, they were actually counting. The reason they were interested because they really wanted to count the number of finite dimensional representations. That was essentially the goal of the paper, which was in turn a conjecture by Ettingov. So the answer was extremely complicated. It relates to affine Lie algebras and lots of stuff about category O for affine Lie algebras. But along the way, they needed, in the proof, they needed this fact for some very concrete case. And finite dimensional representations are, because they were interested in finite dimensional representations, they had this case. And now, as you see, this zero fiber is kind of the most interesting fiber. It's kind of zero is the most singular point of this cone Y. And so the fiber of that point is kind of the most interesting fiber. In particular, all generic fibers, the map is birational from X to Y. So generic fibers are just, it's a bijection. So as the more you approach the zero, the larger the fiber is. And so this zero fiber is the largest possible fiber. And so the sheaf support on this fiber are kind of the most interesting ones.
So this cis direction, does it contract some sense, or maybe there is another cis?
In Y it contracts. If you're not sitting on the zero fiber, your module cannot be finite dimensional because the support is not compact. So this essentially, the reason is that because of this C star action, the only C star stable compact set is the set which is contained in the zero fiber. Otherwise, the C star action, move it to infinity, then the support is not compact, and therefore the space of global section cannot possibly be finite.
Yeah, you see for symplectic topologies, because there are some in the audience, there is this, I think, Liouville action which contracts to a Lagrangian skeleton.
Yeah,
And so it looks like it's
I'm not sure it's exactly this, but it plays a similar role.
Yeah.
So it's it's a kind of Lagrangian skeleton in some sense, but well, I cannot. That's what it is.
Okay.
But it is extreme. It's the most singular fiber. So somehow, and it is indeed extremely crazy. For instance, as you see, if you want to, I mean, the number of linearly independent cycles is less than or equal to the number of irreducible components. Well, this is clear. In particular, the number of finite dimensional representations is less than or equal than the number of irreducible components of this fiber. This is already a non-trivial result. For instance, in the case of the Springer resolution, I believe this was one of Lustig conjectures, which was eventually proved by Bezrukavnikov, essentially secretly using a similar strategy. So it's a highly non-trivial. The fact that this characteristic cycles are linearly independent really implies lots of completely non-trivial things. Well, combined with other non-trivial things, it's a very non-trivial. I mean, it gives a upper bound on the number of simple modules just by geometry of the single fiber. So it's a very kind of important.
Yeah, but what I kind of miss, they wanted to count this, but does it really give a count? I mean, like if you have an irreducible component.
They prove that the upper bound is attained by proving inequalities in both ways.
But is it exact, like to every component?
This is what we would like to do. You would like to prove that every irreducible component or something like that could be quantized. This is false. There are examples.
This is false in what generality?
For Lie algebras, in the case of Springer resolutions.
Because you see, I recall that speaking to Gukov, and well, he's a physicist, and they're kind of maybe writing, at least he promised, a paper which addresses Cherednik finite dimensional representations of Cherednik algebras. And the picture was very much similar.
Well,
you have some similar.
Maybe I'm rude, but I would say that physicists know nothing about this particular issue. And they cannot possibly say anything because it's related, for instance, in the case of Lie algebras, it's related to this theory of Kazhdan-Lustig cells in the affine wild.
No, they don't know. They just establish, but they are good in computation. They do not make mistakes.
The point is that there is no geometric way to give the answer unless something special happens. So, for instance, in the special case of Bezrukavnikov was interested in, the number is indeed equal to the number of irreducible components. But there are many examples where it is not. It is strictly less. And there is no, the number is not, as far as I understand, from all examples I know, there is no geometric invariant that will tell you what this number is. It's not geometric. It's like Kazhdan-Lustig theory. It's not geometric. There's no geometry that would explain your Kazhdan-Lustig theory.
No, I understand. It's a kind of a quantum question, and not every quantum question can be spelled out quasi-clearly.
So it's a good upper bound, which sometimes is attained in nice cases, but there are equally important cases where it is not attained. So that's life.
Yeah, good. So this is your last slide. Yeah,
that's it. Yeah.
But this you already said it. Yeah. Well. Yeah. Thank you very much. So questions, please.
Seems like all people died already.
No. I mean, I see almost everyone survived, and I see that some people who might have questions. So for me, sort of, I understand kind of the point of this theorem, but there is also a question about this category of holonomic, at least holonomic DQ modules. And so then not everything is clear.
I mean, Kashiwara in the on the quantized on the side of on the algebraic side, not on the Fukaya side. I mean, basically, people know what to do, and it's
no. They know only when support is smooth. If it's not smooth, they don't know.
No, I mean, they don't quantize, but what is this category? What category to consider is there's no problem with this. I mean, you don't have, it's known what category.
Yeah, I understand what you mean. You just consider those which are mod H bar has Lagrangian support, no matter singular or not. Yeah.
The point is, when you invert H bar, you have to be careful because you have to be careful how to define the category.
No, but there is, I think there is kind of one more issue which is hidden in this C star action in your case, because you have some canonical compactification. But in general, you can make this compactification a variable. You can choose different compactifications. You will have different categories of holonomic model. Like for the cotangent bundle, there is a natural compactification, which correspond to the growth toward.
But I really don't quite understand the question. We can consider D modules on a non.
Let me give you an example, and so you can.
Somehow people consider D modules on a non-compact variety.
No. D modules, not D module. Let's consider C star square. It's certainly a algebraic symplectic manifold. And well, it's not about D modules, it's about QD modules, of course. It's trigonometric case. But now the question is how to compactify. There is no God-given, there are at least two obvious C star actions. You can choose either of them. But on the other hand, C star square, the torus, is an open part of any toric surface. So then you can choose any toric surface and it gives you the corresponding category of holonomic modules over the quantum torus, I would say, because the quantization is a quantum torus. Yeah, and so then I'm just wondering, your general theorem is a general theorem, yeah. So
well, I mean, I don't know. I mean, I don't have, since there is no formulated questions.
No, there is no question, but if I go
like higher, it sounds like something related to cluster algebras.
No. It's okay. Anyway, it's kind of it's out of the scope of your doc. So more questions.
Victor, I don't have a question. So here, that the algebra B can have many different choices.
No, algebra B is just the global sections of my sheaf.
No, the script actually shows the sheaf, the filtered the quantization. You can have many different and
quantizations by H2. What it's written, I opened this page. It's completely known. Everything here is completely known. For each element of H2, there is a curly B, and therefore there is a straight B. So we know
that's all possible B.
Yeah, these are all possible B. We know exactly how many, namely second homology of X. So it's extremely complete. For example,
I don't have a question. It's the backward. I don't know what the X is, but I don't know what the Y is. Also
give 3 examples. I don't know. In the case of the Hilbert inferences, H2 is one-dimensional, so there's only exactly one parameter family, and this is real Cherednik algebras. In the case of the Kleinian singularity, I think, well, it depends on the group gamma. The group gamma, finite subgroups of SL2 are by Plato and so on are classified by Dynkin diagrams. For instance, if you take Dynkin diagram of type A, so then gamma is a cyclic group of order n. then I believe H2 is n dimensional, or maybe n plus 1 or n minus 1. So we have n or n plus 1 parameters for B. In the Nakajima case, it's more complicated. Again, it's known what it is, but again, so it's this H2 is known, and it's so we know exactly how many algebras B do we get, and the question is how to study representations of these algebras, in particular finite dimensional representations.
But the fiber of the zero fiber, which does not depend on the algebra.
The zero fiber, yeah, the zero fiber is completely geometric. I mean, X is
it's completely geometric, which has nothing to do with this the quantization B.
So what happens? Maybe yes, I get your point. So the point is this: that if you take, so we have this H2. Now, for each element of H2, you have an algebra B. But if you take random elements of H2, then there will be simply no finite dimensional representations at all. Finite dimensional representations only exist for some very special elements of H2. So maybe this is actually what somehow. So this upper bound, if you take generic element of H2, the upper bound is still the upper bound, but it bounds 0. So there are no finite dimensional representations.
I see. Okay.
But even if you take the special value, so then so it becomes, we know what these special values are, but then even if we know what they are, it's still not clear how many finite dimensional representations do we have. Even if we know precisely for which elements of H2 we have finite dimensional representations. So, so this upper bound is interesting, even if we know exactly when do we have finite dimensional representations.
Okay, thank you.
For example, maybe, so for Cherednik algebras, I think one can say exactly, but if you deform a little bit, so if you replace Cherednik algebras by double affine Hickey algebra, which is probably what Cherednik actually was before. But then the number of finite dimensional representations was actually something which Cherednik tried to find a long time, and the answer is very, very complicated.
But there are some other interesting representations like Verma modules which are not finite dimension.
How many doesn't, there's no
question. No. If you want to count, yes, but kind of if you want to have a theory in the spirit of Bellin-Swinburne-Stein.
I mean, people try to develop, I mean, something is known, but I mean, again, at some point, if you want to really, for instance, so, I mean, we know what is a Verma module. We know that any simple module in a reasonable category is a quotient of a Verma module. But the question is,
what's a Kazhdan-Lustig problem with general?
We end up with the same thing. Kazhdan-Lustig is not geometric. So then what do you want? Kazhdan-Lustig is, the answer is formulated in terms of roots, the Weil group, and so on. For a symplectic solution,
you go to perverse.
But it's not clear what language do you want to use. Somehow this is one of the problems. You first have to develop a language. Otherwise, how do you formulate the answer, even if you find it?
Vita, if I may insert a small comment related to physicists, I think I finally understand what you're after. So in case of rational Cherednik algebra, if I remember correctly, there is a parameter called C. You have a finite dimensional representation when C is rational.
Well, it's not rational if you're Cherednik. It depends on, first of all, Cherednik algebras depend on.
For the Hilbert scheme.
No, for the Hilbert scheme. Okay, so this corresponds to type A. So then there's indeed the one.
That's the only one I know.
And in this case, the answer is no. Namely, well, first of all, the Hilbert scheme involves number n, the number of points.
Yes.
And then I think the answer is that the finite dimensional representations correspond to the parameter C, which has the form
m over n.
Yeah.
No, well, first it has the form m over n, but m has to be prime to n.
Yes. And
that's the answer. Then you can ask what is the dimension. It is known. Well, no, for each such see there's exactly one representation,
yes,
which agrees here with the fact that there's only one irreducible component. So in
yes.
fact, is
And the physicists may tell you that this representation is due to the existence of a torus knot of type M comma
yes,
N.
that's what I was going to say, that this is related to knots, knot theory.
Algebraic knots.
Actually, I'm working with one of my graduate students exactly on one conjecture by Gorski, and probably Negut's related to this knot stuff. So
There's a physical argument why such a knot would produce a module over quantized algebra of functions over the Hilbert scheme. The quantization is related to the construction of torus knot by twisting points sitting on a circle as you go around.
Well, it's not a circle. Well, I mean, a torus knot, as far as I know, appears. I'm not an expert in this subject at all, but as far as I know, knots appear as from braids by
closure.
Closing the braids.
Yes.
Now, the braid group is related to the while group, so it's a more refined version of the while group. So it's not very surprising that the braid group appears. And in fact, if you do D modules, I mean, Bernstein or Bezrukavnikov, you see that the braid group does appear. It's not only the while group. And the braid group appears as functors acting on the categories we're interested in, basically on these coherent sheaves on here. So, well, then you still can ask, how do you see the Hilbert scheme out of it? And this is a kind of a puzzle, which I don't have an answer.
The Hilbert scheme itself or the punctured Hilbert scheme, I forgot.
It doesn't matter, it's not very important. But the question is basically, how do you see, why does Hilbert scheme appear in anything I said before? There are, as far as I know, there are two. Well, it's not two, there are, okay. It's one answer, but it's kind of, the point is that if you look, the Hilbert scheme is a Coulomb branch of something. Well, in fact, in this case, sorry, no. Yes, okay. So the Hilbert scheme is a Coulomb branch of something. But now if you look at the definition of what Coulomb branch is, in this particular case, it is something related to the Hecke algebra. Just by definition, if you look at this BFM mathematical definition, it involves the affine Grassmannian. And for this particular case, and as for basically, for this particular case, the definition reduces to the affine Hecke algebra. So it's not very surprising that, but I mean, I don't know how satisfactory this is. And the quantum Coulomb branch gives you the Cherednik algebra. So the theory is, I mean, everything matches here nicely, but it doesn't explain in some sense why do you get not invariance from this. And in fact, it's very mysterious.
I hope to explain this in 1 week.
Yeah, it just happened.
I spent a year trying to understand this, and somehow we failed. Well, we know I know this stuff about, well, I heard this stuff about matrix factorizations, but I'm not very happy with this. And so, but it seems to be. So anyway, we can talk about it sometime. I guess. No.
Example during the next weekly of stocks.
Yeah, sorry. Actually, I was thinking of calling you and asking this the same thing, but I'm afraid that
you're welcome 24 hours a day, 7 days a week.
I'm just.
How many hours today? 24. Okay.
Yes.
I don't think there is any good answer, so even if I call, so I decided not to call right now. So anyway.
All right. More questions to this discussion, or maybe to any other discussion? Okay, last chance. Well, if not, let's thank Victor for very, very interesting talk, very inspiring. Thank you very much.
Okay, take care.
Okay.
Thank you, Victor. That's all.